Okay, now that we know how to draw a block diagram and what are the components of a block diagram, so the next thing that we will be talking about will be how can we solve them? How do we simplify complicated block diagrams into more simple block diagrams so that we can determine the transfer function of the whole system, the output divided by the input of the full system. So in general, a block diagram, you have two blocks generally, most common in the forward path. We call this one the forward path. So we have a signal input, then we have here connected. Then this one is usually the control element. So just like our example in the previous discussion element. So this is the DC-DC converter, or mostly we use controllers here. We use PID controllers. We have the lead and lag compensators and so on. So there are controllers. So you control the plant, which is this one. This is the plant. So we call this one the plant. Plant is the system that we're controlling, or the process that we are controlling. So in our case, in the previous example, that's the motor, the DC motor, while the device that we use to control that is the DC-DC converter. Then the output here will be, we call it C. Then we have a summing point somewhere here, because this is a feedback control system. It's a closed control system. So this is our R. So we have a feedback, another block here, and we have a point, take a point, then this is the feedback element. Feedback elements usually are sensors, transducers. Feedback element. Then the output of the feedback will be feed into the summing point here, and we can call this one the B. B here is, this is the primary feedback signal. Primary feedback signal. So these are signals. Feedback signal. Well, R here, this is our reference input. So this is our input, reference input. A reference input. This is what we want. Well, C is the actual output. So this is the actual output. Then this is always plus. This can be minus plus, the feedback. Then here we have a letter E. This letter E, we call this one the actuating signal. E here, this is called the actuating signal. Or we also call it the error signal. Actuating. Or the error signal. And basically, it's just equal to the sum of R and B. So R plus R minus plus B. It's the difference. Then that will be the input of the control element. Then for the control element, it has an output again. We usually call it U. And this output, this is what we call the control signal, or manipulated variable. Some books uses manipulated variable, or control signal. Control signal. Then also, in real control system, there are some disturbances or noises that's going to our plant. So these noises these are unwanted signals. These are unwanted signals. We don't want them in our system, but because of reality in real control system or circuits, there are always be noises. That's the effect or the factors outside our control or outside the plant or the process. Then we have the output C, then it will go back here. so on. So now, this one, the path from the input to the output. So we call this one the feed or the forward path. We call it the forward path. These are terms, basic terms. It will be very useful later on when we are solving some problems. Then, for this one, from here and go back to the input, this is the feed or feedback path. They call it the feedback path. So forward path is the path from the input to the output, while feedback path is the path from the output to the inputs the other way around. So this is the basic common control system. But in reality, we don't write them. We don't use control element to write on the block diagram. We represent, we use variables to represent them. So usually in a feed forward path, we use G as our variable. Or this is a transfer function. This is the transfer function of the control element. We can call it G1 because there are two transfer function in the forward path. And this one we just call it G2. Then we have here R, and this is U, and this is E. And we have here for the feedback we use H. Then output, go back, feedback. So plus, minus, and plus, and this will be our output. This is the general block diagram. But this is the most simplest form of a feedback control system. And just like what I said before in the previous lecture, there is what we call the canonical form. Canonical form. What is a canonical form? This is the simplest form of a block diagram that has a feedback path. Because the most simplest form, of course, is just an open loop control system. This is the most simplest form. But if you include the feedback, then the simplest form is, we call it the canonical form. So we have one transfer function in the forward path. Then we have also one transfer function in the feedback path. So we have a feedback, so we need the summing point. And this is our input, or then we have here B, and this is our C. So this is plus, this is minus, plus, and this is E. So now there are different parameters that we need to know here. G here, we call this one letter G. So basically, for example, this block diagram, the forward path, it has two transfer functions, G1 and G2. But we can solve for the equivalent of that, or simplify this two cascaded blocks into just one transfer function, which is equal to G. And we call this G is called the forward transfer function. Forward transfer function. This is the transfer function in the forward path. Function. While H is the feedback transfer function. This is the feedback. It can also have more than one block in the feedback path. Feedback transfer function. H transfer function. Then if you multiply G and H, G times H, that is what we call G times H. This is what we call the loop transfer function. We call it the loop or open loop transfer function. TF. Then how about the total transfer function? C over R. Output over input. How do you solve for the output over input? We call that the closed loop transfer function. See, C over R. This is the closed loop transfer function, or some books uses they call it control ratio. C over R, output over input. Then if I divide the error signal E with the input R, this is what we call the actuating signal ratio. Actuating signal ratio. Or simply, this is simply called the error ratio. Error ratio. So if we divide the error with the input, and if we divide B, what is B? B is the feedback signal with R, then this is called the feedback ratio or primary feedback ratio. So these are some parameters that we need to look at in a canonical form. So if you have a canonical form, you can derive this value of these different parameters. First, for C times R, what is C or C over R, the total transfer function? So remember our definition here. So if I have a transfer function G, this is R, input, this is C. So if you solve for C, C is just equal to the input of that transfer function times the transfer function. C is equal to R times G. So we apply that in this case. So if I solve for C, so at this point, this is C. What is C here? That's the output of G. Okay, so the output of G is C. What is the input of G? It's just E. So here, this is just E times G. The output of G is just equal to the input times its transfer function, just like what we did here. C, the output of this one is just equal to this one times this one. So E times G. So C is just equal to E times G. And this is a take-off point, so they are the same. This is C also, this is also C. Okay, they are all equal. But E, we know that E, what is E? E is just equal to the sum of the input R and the feedback signal. So this is minus plus, so minus plus B. So E is just equal to R minus plus B. So here, this is, we can substitute that. So this will be R minus plus B times G. Then we go back. How about B? What is B? B is the output. The output of what? Output of H here. What is the input of H? The input of H is C. So therefore, B is just equal to the input, which is C, multiplied by that H. So B is just equal to C times H. Then we substitute it here again. So this is C. Then R minus plus, our B is now C times H times G. And we can distribute this. So this will be equal to RG minus plus C times G times H. And this is C. Now, if I put C, G, H on the other side, this will become, instead of minus plus, this will become plus minus. We multiply it with a negative. C, G, H equals R times G. And I can factor out C here. So we have 1 plus minus G times H. And this is equal to R times C. But we want to solve for C over R. So I divide both sides by R. So we have C over R. Or wait, this should be G here. This is not C. This is R times G. So if I divide both sides by R, so C over R, and I also divide it by 1 plus or minus J, so this will be equal to, here we only have G, because I divide it by R, and here I need to divide also this one by 1 plus G times H. And this will be the formula. So you can remember this formula. This is the transfer function of the whole system in canonical form. You just take the transfer function of the feed forward or the forward path. You divide that with the 1 plus or minus. It depends on the sign here. So if it's a negative feedback, this should be plus. If this is plus, this should be minus. It's the opposite. G times H. G times H is the closed loop or the open loop transfer function. You just multiply these two, and that will be the product G times H. And that will be the transfer function of the whole system. So just like our example, in here, you just need to simplify first this. Then if you know that G in that, the equivalent of that, then you can now solve for C over R. in terms of G1, G2, and H. But what is that G here? How do we simplify this, G1 and G2? But before we do that, how about E over R? So let's derive it again, E over R. What is E? So we need to solve for E. So we just E over R. So E is this equal to R minus plus B. But B, what is B? B is C times H. Or we can do the other way around by solving E here. So we know that E, this one, C is equal to E times G. So if I solve for E in this case, E will be equal to C over G. But what is C? C, somewhere here, is 1. In terms of B and H, so again, that one is B is equal to C times H. Here, solving for C, C will be equal to B over H. So I just substitute here. So this will be B over H all over G, or simply B over G times H. Then for B, in this case here, if I solve for B, so this will be minus plus B equals E minus R, E minus R, or B now will be equal to minus plus of E minus R. So that's B. So our E here now will be equal to minus plus, that's our B is E minus R all over GH. Or this is just the same as E minus R. We can put the minus plus at the denominator, minus plus G times H. Then cross multiply, so this will be E all over E minus R equals 1 over negative positive G times H. Inverse this, E minus R all over E. So we also inverse this one. This is this minus plus GH. And this will cancel. 1 minus R over E equals minus plus GH. Then if I solve for R over E, I put it to the other side, it will become positive. This one, I put it to the other side, it will become plus or minus. So 1 plus or minus G times H. But what I'm solving is E over R. So you inverse it again. So E over R now, the error ratio is just equal to 1 over 1 plus or minus G times H. So this is another formula, the error ratio formula, or the actuating signal ratio. For B over R, you can also derive this. Try to derive this one on your own. And the answer will be B over R is just equal to G times H all over 1 plus or minus G times H. You try to derive this, you do the step that I did here from the previous examples here for the error ratio and the control ratio. So these are the formulas for the different parameters that you want to solve in a canonical form. But the problem is, how do you simplify them in the canonical form? That is block diagram reduction. That's our actual topic. So first one, so these are the rules that we need to take into consideration when we are simplifying. First one, cascaded blocks. Cascaded blocks or series blocks. So if we have 2 or more than blocks that are in series, so let's say this one is G1, then we have another G here. So these are two blocks. It can be more than 2 if you want. So let's just take the 2. If I have here my input R and this is my output C. So if what we want is we need to simplify this into a just single block. because we are simplifying. We are reducing the block diagram into a simpler form with input R and output C. So here, we need to solve for what is the signal here? It will be R times G2. R times G2. Then if I solve for C here, C will be just equal to the input, which is R times G2 times the transfer function. So R, or this is G1. This is G1. So this is G1. R G1 is the input, while the transfer function now is, so this is RG1, and the transfer function is G2. So if you look at here, we just need to, so C, we can G1 times G2, and this is our input R. So therefore, so if I take this as G1 times G2, then if I solve for C, here, C will be just equal to R times G1 times G2. G1 times G2. That's the transfer function, the forward transfer function, G. Then if you look at, they are just the same thing. So, conclusion, and therefore, there are the same block diagram. They represent the same thing also. So in general, so if you have more than two cascaded blocks, so what we do is just, if this is G1, then we have another block G2, then another block dot 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 up to, let's say, Gn. And then you have an input R, then you have an output C. So the simplification of this into just one block with the input R and output C is just equal to G1 times G2 times G3 dot 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 until Gn. So that's how we simplify cascaded blocks. We just multiply the transfer function in the same path. So in this example here, G here will be just equal to G1 times G2 because they are cascaded blocks. Okay, so that's the first rule, cascaded blocks. So this is blocks in series or cascaded blocks. Next, how about if they are in parallel? Number 2, parallel blocks. How do you simplify parallel blocks? Or what is a parallel block? When can we say that two blocks or more are in parallel? They are in parallel if, so for example, we have two blocks here, another block here, then we have an input somewhere here, input R, then this is also connected to this one. Then there's a summing point somewhere here, and it's connected to that summing point. This plus, plus, and this will be our output C. So if this is G, let's just call it G1 and G2. Again, G1 and G2. They are both in the forward path. Now, it's just like the inverse of a canonical form. So it's not canonical form. Remember, this is not the canonical form. So if you look at the canonical form, here, the input is connected to the summing point. But in this diagram, the output is connected to the summing point. It's the other way around. The summing point is at the other side. It's at the right side. So what will happen if this is the case? So don't use this formula here, G over 1 plus minus GH, because it's not true. It's a different formula. It's a different case. So to derive the equivalent of this, and remember, what we want is we simplify them. We want them to reduce into just a single block. A single block R, input R, and C. But the problem is, what should be the transfer function of this block here? So how do we do that? We just need to solve for C in this case. So remember, at G1, transfer function G1, the input of G1 is R. It's connected here. This is also R. While the output is somewhere here. I don't know the output here. But I can solve that. It's just equal to R times G1. It's the product. Okay, remember that. So this will be the input somewhere in the summing point. Then for G2, the input is still R. So the output here will be R times G2. Then if I solve for C, because this is plus and plus, C will be equal to the sum of the two signals, RG1 plus RG2. And here we can factor out that R. So this will be G1 plus G2 times R. And look at that. This part here will be our transfer function. So in this case, the transfer function of this block sum in here will be just equal to G1 plus G2. Why? Because if we solve for C here, we just multiply these two. So R times G1 plus G2. And it's just the same thing. They are just the same thing. So the equivalent now of these complicated parallel blocks is this one, G1 plus G2. So if you have another block somewhere here at the bottom, G3, then what you do is you also add them. So you add them all, G1 plus G2 plus G3. You multiply it with the input R, then that will be our output C. That's the parallel blocks. So that's how we simplify parallel blocks. Next, if we want to move, number 3, we want to moving the takeoff point. Takeoff point from left to right of a block. So let's say we have a block here. Let's call it G. Then we have an input, or then we have a takeoff point at this point here. That's going into that direction. I don't know if whatever the input or the block diagram here or the block here, as long as it's a takeoff point. So this is R here, and this is also R. And we have an output C. Now, how do we, so we move the takeoff point. So remember, we want to move the takeoff point from left to right. So from here, we want to move it at this point here. That takeoff point somewhere here. So we need to, let me draw this. Convert this into, this is G, this is C, and we just make our takeoff point somewhere here. So originally, our takeoff point is at the left of G. Now we want to convert it, transform it, or transfer it into the right side. And what will happen? Now, take note of this. We have still an R input. This is not true. We cannot just move the takeoff point without doing anything into the block diagram, because if you remember, what will be the output here? The output here will be R times G. But you have a takeoff point here, and we know that this takeoff point will be C. And if you look at the original one, the takeoff point, the signal coming from the takeoff point is R. But in this case now, it becomes C. And that is not correct. So what we do to compensate that is we add another block somewhere here. So if I write another block, and the output here should be equal to R. Why? Because just like the original one, we have an input R, we have two outputs, C, and this one should also be R, because that's the takeoff point. Now, what will be my transfer function here so that my output is R? And remember, here, this is C. So if I solve for R, I just need to multiply the input times the transfer function here. So what should I multiply to C so that the output is R? So that the output is R. So I need to multiply it by what? And if you remember, C is just R times G. So here, the C here is R times G. So what do I need to multiply R times G to get R? That will be, I just need to multiply it by 1 over G. We just need to cancel out that G here. So if you multiply them, RG times 1 over G, that will be just equal to R. So in conclusion, if you want to move the take-off point from left to right, you just need to add another block at the branch here, at the signal here, and the transfer function of that signal should be equal to the inverse of the transfer function of the forward path transfer function. So even if you don't know this one here, you can just remove them. You just need to multiply this by or put transfer function here by 1 over G, and therefore these two will be equal, exactly the same. So that's how we moving a takeoff point from left to right. Now for the other way around, so if I move a takeoff point, but this time instead of from left to right, I move it from right to left. From right to left. Instead of left to right. From right to left of the block. So in this case, so we have a transfer function or block here, and originally our takeoff point is somewhere here. Then we have another signal that's going here. So our input is R, our output is C. You know that this is also equal to C. Now, if I want to move this point and put it on the other side, so from right to left of the block. So if I do that, so this is still G, and this time the takeoff point now is somewhere here. Then I still have my signal here. This is R, this is C, G. And in this case, again, if you look at this signal here should be R. But we want it to be C so that they are equal. We want it to be equal. We just move the takeoff point, but we don't need, we should make the system to be the same system. So the output should be the same as the output, the input should be the same as the input. And whatever inside between, whatever in between them, it doesn't matter as long as the output and the input are the same. So we need an output of C because this is C. So I need again to multiply it with a transfer function so that this one is C. So what should I multiply? R, so that I get C. But remember, R here is just equal to what? R. C here is equal to R times G. So if I solve for R, R is just equal to C over G. So R here is C over G. So my input here is C over G. And I want my output to be C. So what should be the transfer function? What should I multiply C over G to get C? Of course, I just need to multiply it by G. So the transfer function here is just equal to G. You add another block, and the transfer function of that block is just equal to G. So that's how we move a takeoff point from right to left. This is from right to left. If it's left to right, you need to multiply the signal here by 1 over G. The one that we are moving. Remember, this is the one that we are moving. So we need to multiply on that path with the inverse of this transfer function where we are moving. So this is we are moving this one, so we need to compensate it here, and the one that we are be putting here should be equal to the transfer function that we are moving from. So in this case, this is from right to left. So I need to multiply this path by G here. Okay. Later on, we will have more examples here to reduce some complicated block diagrams. You will appreciate this rules. You will understand them more, but you can also memorize them if you want. But I don't suggest them for you to memorize them. You can just analyze it, just like what I'm doing right now. Now, what if the point that I am moving is not a takeoff point, but it's the other type of point. We call it the summing point. What if I'm moving the summing point from left to right and right to left of a block? But instead of a takeoff point, I'm moving a summing point. So let's call it number 5. What will happen? So instead of the takeoff point, I just remove this and make it a summing point. So you already know what is a summing point. That big circle here, this is a summing point. Some books uses X, they put X in that. It's still the same. So if I want to move the summing point, so let's say this is from left to right, from left to right. So if I have a block G here, then I have a summing point somewhere here. I have an input, then I have a signal here. And if this is plus, this is plus. Then this signal, let's call it B. This is the feedback signal usually. This is OR. Then we have an output C. Now I want to move this one. I want to move this summing point into the other side. I want to move it into the other side. So if I draw this again, this is G. Now the summing point is somewhere here. But again, this should again be equal to C, so that we don't change the block diagram. Then I still have an input here, and this is still B. And I still have an input R somewhere here. But again, this is now here. This will not be equal, or this one somewhere here will not be equal to C, because this is B. The output here now is R times G, R times D. Then if you add it with B, then that will not be equal to C. Why? Because our C should be equal to here. Remember, our C here is, what is the input here? There's the sum of the two, R plus B. So the output is just equal to R plus B times G. So we need a C here that will be equal to R plus B times G. So if this is the case here, we have RG plus B, if this is plus and this is plus. And they are not the same. So to compensate that, we need to make it equal. We need again to add another block from the signal or the path that we are moving. So the path that we are moving is this one. So we need to multiply this, or put a block here. And this is B here. So that the output here, if I add it with R times G, it should be equal to R plus B times G. Or this is can be also written as, so you can see this. This can be written as just R. You can distribute the RG plus B times G. So we already have RG. So we need here a B times G. So this should be B times G, so that my output will be RG plus B times G. And they are, again, be the same. So if they are the same, then this is correct. But what should be the transfer function here? How do I make the output be equal to B times G? If my input is B, I just multiply it by G. So B times G is the output here. If I add it with RG, then that will be our C. So if you are moving a summing point from left to right, so I'm moving a summing point from left to right, you need to include in the path that you're moving a transfer function that is equal to the transfer function of the path that you are moving. So if you go back here in the takeoff points, in the takeoff point, when we are from left to right, we put 1 over G. But here, if we're from left to right, it's the other way around. You put it G. It's just G. So in next case, so if we go from the other direction, instead of, so number 6, left to the right, we make it right to left. So this is right to left instead of left to right. So again, a transfer function. So from right to left. So the transfer function is originally somewhere here, or the summing point. Then we have let's call this one again B, and this will be our C, and we have an R here, input R, and let's just assume this is plus and plus. And remember, if this is not plus and plus, this also changes. If this is minus, then this will be minus B times G. So instead of somewhere here, here, if this is minus, then it should be minus also. So it's just the same. Then, in this case, we want to move the summing point from left to right. So here is our summing point, yung summing point. And again, this is OR. Then we have here, this should be B. Then we have an output C. And this as G. So we need again to compensate that with the transfer functions here. So this is plus and plus. Then what should be this one, so that if you add it with OR, the output here will be C. And what is C? Actual C here is, if you solve C here, in terms of G, and this is R times G, and this is B, so C here will be R times G plus B. So that's the output that you want also in this part. But if you do that, if this is not in the transfer function or in the diagram, we just insert here B. This will be R plus B. Then if you multiply, your C will be R plus B times G, which is wrong. This is not true because it should be R times G plus B. This is RG plus BG, so it's not correct. So we need to add something here so that if we add it with OR, then you multiply it by G, this will result to this one. So what do you think? So if, again, it's should be in terms of G. If I already used G here, so obviously this should be 1 over G. If you try that, this is 1 over G, so this one will be B over G. So this one is also B over G. Then if you solve for C, you multiply this with G, you distribute G, it will be equal to, so C here now will be equal to R times G. Then B over G times G is just equal to B. And if you look at them again, they are the same. So this one is moving from left to right. So you just need to include 1 over G, a transfer function that is equal to 1 over G, so that your output is still the same. Okay, this is how we move summing point. This is how we move takeoff point. Now that you know the concept here on, these are different rules. You don't need to memorize them again. You just need to understand the concept. You need to, the important thing here should be the output and the input of the one that you are simplifying should always be the same output and input of the simplification. So you can just manipulate them if you want, as long as the output and input are still the same. You can even move or switch between two summing point if you want to switch them. Move to the right of summing point to the left of summing point. Even a takeoff point, you can move it around a summing point. But it will be you need to apply more calculation, more analysis to do that. So now that you know this, the next thing that we'll be doing, we'll be having some examples on how to apply these things in reducing block diagrams, complicated block diagrams. Okay?